Okay, so the plan for today, the remaining plan for today, is to talk about just in general how to orient yourself on Unix machines, on Linux machines, how to sort of do the basic things you need to do in order to use the machine, and also to work with image files. I'm just stalling so I can get my file. And so I tried to break. Well, we've broken this up into three parts, and I'm doing the first part, which is basically just command line stuff, how to work with images and the Unix command line. After which, Hoon is going to get some background on registration, which is the real overarching topic for today. And finally, Ol is going to tell you actually how to go about registration. Okay, so I better sit down. This is going to get complicated. So what I'm going to try to do is actual. I'm going to try to actually show you what I'm talking about as I'm doing it, so that it's slightly less mysterious. But you don't have to remember everything I'm going to say because. Because what I've done is I've made a cheat sheet, and if you could just memorize everything you see there, you'll be fine. It's a two-sided cheat sheet, and it's actually pretty useful, I think, to the extent where I think I may make myself a copy because I put a lot of things in there that I'm always looking up, and some things that I'm not. But I will put that up on the website in the next couple of days. I can't resist continuing to tweak it. But it has one side that's mostly about using Linux and using the command line, and one side that's mostly about using voxel and other command line utilities under Linux to do image processing. And it's got a whole section listing all the broadband areas, which I found helpful. But anyway, the first thing I want to mention is that when you start using Linux machines, the biggest difference between using them in Windows machines or Macs or whatever is that you spend a lot of time at the command line. The biggest sort of underlying difference that's really different from between these two architectures is one that people often describe as the sort of central Unix philosophy, Linux being a derivative of Unix, which is that programs are not meant to do huge monolithic complicated things, but to the extent possible, the idea is to design software that that's broken up into little programs, each of which does one thing really well, or two things really well, or something like that. The idea is to make things as modular as possible so that you can recombine them in lots of different ways to do what you really need, without necessarily having to write your own new program. And to some extent, the image processing software that I've developed follows this in this mold. It's mostly, but not all of it, done at the command line, which in Unix is referred to as the Unix shell. And there's a specific shell that we typically use in Linux, which is called bash. There are lots of shells. Bash is the most popular. And if you have an account on the machines here, or the machines at Penn, or some machine, or the virtual machine that I put up, and you log into the machine and open up a terminal window or a command line window or whatever. Bash is what you'll be using by default unless you make a special effort to change it. There are lots of common shell commands that it's important to get familiar with. These are all in the cheat sheet. But I divide up into a few groups just to sort of emphasize points about these. The first row is just basic getting around in a Linux machine. So actually I have a little list of the commands that I wanted to sort of demonstrate as I'm doing things. So, there are little commands like cd takes you to your root directory, and cd to VLSM workshop changes to the directory that has the files that we're using today, and ls to list your files. So just basic things like that you need to be familiar with. PWD to show what directory you're currently in if it's not obvious. So there's a lot of these sort of basic commands that if you've ever used any command line interface before, it's just little things that you need to learn. The next most important command that I would say is really important to learn on a Linux system, and that I would encourage you to really remember when you need to, is the man command. Man is short for in Unix for manual, and you can see the manual page for any program that you're interested in. So if you can't really remember all the details about how ls works, you can just type man ls like that. Should I make this font size a little bigger? And you can get a little description of all the different arguments, all the different options for ls and what they do. And especially once you're fluid with working with these commands, this becomes a very useful reference. The other thing you can do is type man-k directory. That's just going to show like a ton of stuff. But what it basically does is shows you all the commands that are relevant to the word directory. So if you know you're looking for something that removes directories, you can probably find it here. Maybe. There it is. RM. Or RM there. Anyway, I just want to emphasize that because a lot of people flounder on Linux for no good reason because they can't remember to use to look at the man pages. The rest of the stuff I'm not going to go through in detail. It's all in the cheat sheet, but it basically tells you how to get through the command line without going completely insane, and also how to do things that I think people frequently need to do and don't know how to, and they just assume are not possible, like searching for files by some sort of pattern or by modification date, or checking to see how much space is being used by a directory. So, as some of you might know, VoxBo is a software package for brain image analysis. It was originally for fMRI analysis that I developed along with Jeff Aguirre and a bunch of other people. Like a lot of Linux software, it's free. In keeping with the sort of Unix software design philosophy, it's modular in the sense that it's made up of probably about 120 different programs, most of which nobody ever needs to use directly. But there's a core of 20 or 30 that even if your needs are relatively modest, they would come in handy if you. It's designed to be interoperable in the sense that it doesn't force you to use VoxBo in order to do imaging. It's designed to work with whatever you're using. So if you're using SPM, there's some subset of those 100 some utilities that will be useful to you. Same with whatever package you're using. It's not designed to lock you in or force you to subscribe to a particular analysis philosophy. And because of the modularity, it's meant to be flexible. It's not meant to commit you to a particular statistical model, although it has a particular set of things that are implemented and things that aren't available. But to the extent that it does offer the options that you need, it's not meant to tell you what to do. I sometimes refer to that as the philosophy of giving people enough rope to hang themselves, which is important because some people actually need that rope to do useful things. Here is a list of important VoxBo commands that again, this is all in the cheat sheet. But I just want to demonstrate how a few of these work, just to give you a sense for what working with image data at the VoxBo command line is like, especially with respect to lesion analysis. We'll put that file. Okay, so I'm going to take this to the left here. Okay. So I prepared this little directory full of images, and we can look and see what files are in that directory. Can everybody sort of see this? We can go to the top. Maybe if I just put the whole window to the top. Okay, so you can see there's a bunch of stuff in this file. There's an AAL file, a Broadband file, a version of the Colin Holmes brain, CH2, a lesions file, and some other stuff. The most useful VoxBo command for just orienting yourself to what's in the directory is VBI. If I say VBI star being a shortcut for all the files in this directory, I can see what these files are. And I made the font so big it doesn't fit on that line anymore. Okay, try Okay, so now I see one line for each file in this directory, and for some of them, it can't read them. So Voxma doesn't know what a .txt file is. It's not an image file. But for most of the rest, it has some idea what they actually are. So for example, it knows that this one is a nifty three-dimensional file with these dimensions, these voxel sizes, and this type of data inside. And so on for the rest of them. You'll see that actually all these files have the same dimensions, 181 by 217 by 181. The lesions file adds an extra fourth dimension because it's a series of volumes. And that happens to be a common dimension for 1 millimeter MNI volumes. The cheat sheet has a list of common dimensions. I find very helpful. I'm always looking this stuff up. So they're mostly nifty 3D files. Here's one file that's in Voxma test format, and it also happens to be 4-dimensional. You can see it has an extra dimension at the end. And for whatever reason, it doesn't have voxel sizes set in the header. And then finally, this file was somehow parsed as a vector. So it doesn't actually say vector, it probably should, but it tells you the mean and variance of it. I can't remember why I created that file, but we can look at it. There's more commands in it. I was trying to demonstrate something about sorting that I think might come up later if I get really bored. Okay, so VBI, very important for getting yourself oriented. For lesion analysis, there is another useful command called VB-maskinfo. You paste this command in here and makes this window a little bigger. It basically takes a lesion file that has a series of volumes. This file has 86 volumes, one for each subject in a particular study that we conducted. And it gives you a summary of what's in the file. It tells you how many patients, how many total voxels are in the volume, how many of those voxels actually have some data in them. It turns out to be a little more than 10%. How many voxels don't have data in them, in case you don't know how to do subtraction. And then finally, this measure of total distinct voxels. So you may remember from week 1 that many voxels in lesion volumes are identical. This tells you how many distinct voxels there are among the 798,000. Turns out somewhere about around 15% looks like. And then finally, a breakdown for voxels with different numbers of lesions. So for example, of those 798,000 voxels that have data, there are 123,000 that are lesioned in exactly one subject, not all the same subjects. Of those, among those 123,000, there are 60 distinct voxels, and so on. So these are things that it's actually helpful to know about the lesion volume you're looking at. In addition to sort of telling you some things about how much data you're looking at, how bad your correction for multiple comparisons is going to be, how granular the images are, or smooth. It can be helpful in sanity checking. It will tell you things that will obviously look odd if you're giving it the wrong kind of data. And actually, at the end, it will give you a warning if you have values in there that have, if you have maps in there that have values other than 0 and 1. It's not that you can't do these analyses with maps that have non-binary data in it, but it gives you a warning just in case, because we frequently don't. So that's VB-maskinfo. It's a particularly useful command for lesion analysis, and when we get to the next session on statistical analysis, it'll come up a fair bit. The other thing that's frequently useful to do is to run this VB overlap command to see exactly where the lesion maps that you have overlap with a given atlas. So I'm going to run this command, which overlaps our set of 86 lesion maps with the AAL atlas and prints out overlaps for each patient and each region in the atlas. What you'll notice immediately about this is that it's a tremendous amount of data scrolling by really fast. Actually, it's scrolling by so fast you can't even tell that it's changing. But it is. If I make some blank lines, it's just going to keep going. Okay. So that could be helpful if you're going to crank it through some other software to summarize it. The other thing you could do is say you're specifically interested in region 3, which I think is a frontal region. And this gives you a more reasonable amount of data. Actually, it's giving you summaries for each of the 86 patients of what the percentage of damage is. Actually, this one do it even wider. And you can see, I'll just stop it, but you can see that for many of them, it's relatively little, but there are some patients, like this one right here, where that region is damaged, is more than 50%.